Now 3C273 tends to be fairly constant in X-ray output, so we have no direct evidence for its size. But in terms of investigating this class of objects, it is clear we have our work cut out for us. We need to explain how they produce prodigious amounts of energy in a very small space. What can possibly allow us to do this? The most plausible explanation for these most implausible objects appears to be, oddly enough, similar to models that exist for binary X-ray stars in our own galaxy. The idea is that matter under the influence of an intense gravitational field loses energy and releases enormous quantities of radiation in the process. Just as water goes over Niagara Falls, losing its potential energy while providing us with power to drive electric generators, so can material fall into a stellar gravitational field and emit light by colliding with neighboring atoms and heating up. Currently, the most popular model is that material near the quasar falls into a black hole. But doesn't a black hole swallow everything around it? This is a very common misconception, and the answer is no. Only material very close would inevitably be sucked into this type of object. In fact, if the sun were suddenly to become a black hole, the orbit of the Earth would not change at all. However, other things surely would change, and in a hurry. How much energy is released depends on the strength of the gravitational field and how much mass is fed into the hole. The black hole really doesn't have a surface, but the material continues to yield energy to the outside world until it passes a place known as the Schwarzschild radius, named after the German astronomer who worked out its properties nearly a century ago. The Schwarzschild radius is the distance from the center of a black hole at which the escape velocity will be equal to the speed of light. Thus, light trying to get out of a black hole will not be able to pass beyond that distance. It will look black, therefore. However, mass trying to get in from the outside will radiate like crazy as it approaches the Schwarzschild radius, also known as the event horizon, and loses gravitational potential energy, again similar to the way that water falling over Niagara Falls loses gravitational potential energy and drives electrical generators. Although a correct analysis of this situation requires using general relativity, it turns out that the Newtonian analog of this problem provides us with the correct answer. By using the principle of conservation of energy and setting the escape velocity surrounding any mass m equal to that of light, we find that the Schwarzschild radius is given by a fantastically simple formula. Schwarzschild radius equals 2 times the gravitational constant times the mass of the object divided by c squared. And that works out to 3 kilometers per solar mass. So if you have an object equaling mass of the sun, its Schwarzschild radius would be 3 kilometers. If you could squish the entire mass of the sun into a volume of radius 3 kilometers or less, you could make it a black hole. Notice this is not the same thing as merely traveling 3 kilometers from the center of the sun, because the enclosed mass at that point is way less than 1 solar mass. For a black hole of mass 10 to the 9 solar masses, 1 billion solar masses, the size is on the order of 10 to the 9 kilometers, which is on the order of the size of our solar system. Furthermore, the energy that a mass of little m can lose when it travels from infinity to the event horizon is given by, and here we'll use the Newtonian expression for total potential energy from infinity, Gmm over r. So now we can estimate the energy output of a black hole by determining the gravitational potential energy lost by a mass m as it travels towards the black hole of mass big M and reaches the radius equal to its Schwarzschild radius. So let's say, for example, that little m is equal to 1 solar mass. Our black hole is about 10 to the 9 solar masses. And the question is, if we have a mass equal to our own sun, and it's gravitationally accelerated from far away to an r sub s of where a 10 to the 9 solar mass black hole exists, in about 1 year, how much energy does the black hole emit under these circumstances? Well, all we have to do is plug in our numbers here, and G is 6.7 times 10 to the minus 8 in these units. Big M is about 2 times 10 to the 42 grams. The mass of the sun, little m, is 2 times 10 to the 33 grams. And our Schwarzschild radius is about 3 times 10 to the 14 centimeters. When you do this, you find out that this energy is about equal to 10 to the 54 ergs. Now, that's over 1 year. If you want the energy released per second, all we do is take this quantity, 10 to the 54 ergs released over 1 year, and divide that by the number of seconds in 1 year, which is about 3 times 10 to the 7 seconds. And lo and behold, you get an energy released equal to, about 3 times 10 to the 46 ergs per second. This is more than enough to power 3C273 as observed. Thus, our picture becomes this. An intense gravitational field provides the pull that sweeps material of mass equal to our sun each year into its confines. The energy released provides the X-rays, radio waves, and optical light that we see coming from the quasar. The variability is explained by the small size of the object. Even though it shines more brightly than hundreds of entire galaxies, it occupies a volume no larger than our solar system. Neat, huh? In fact, it is hard to convey the excitement that the discovery of the quasars generated in the early 1960s. Martin Schmidt's picture even appeared on the cover of Time magazine. But there was much skepticism regarding their true nature as well. Not only were the energy requirements enormous if the quasars were really distant objects, but something else was observed in the 1970s that made the whole puzzle even more unbelievable. It appeared as if 3C273 had yet one more trick up its sleeve, one that threatened to wreck our entire model. What was it? It seemed like some material in the jet was moving at many times the velocity of light, which violated once again all our ideas about the nature of space and time. Remember that we encountered a similar problem with GK Per. Let's look at the radio map of 3C273 taken by researchers at the Owens Valley Radio Observatory and the National Radio Astronomy Observatory. This image is also available to you in the supplementary materials section of the course. Look at the little blob of material that is moving outward. It appears to change its position by 0.002 arc seconds in 3 years. Let's see what this seems to imply. First, let's calculate how far it has moved across the sky in 3 years. So we're going to calculate this distance L, and what we know is that this angle here is 0.002 arc seconds, and we also know that the distance is about 700 megaparsecs. Well, we know how to do all this stuff, right? L must be equal to delta theta, which is what this angle is, times d, where this is the distance. And so L equals 0.002 arc seconds divided by, once again, 206,265 to make this angle a radian measure. And now we just multiply by 700 megaparsecs, which is our distance, but we're also going to convert to light years, so we'll multiply by 3.3. And so this now is going to represent a distance in the unit of light years. Okay, this turns out to be about 10 to the minus 8 radians. And this turns out to be about 2.3 times 10 to the 9 light years, or a distance of about 23 light years. L equals 23 light years. Now, what must its velocity be for this to be true? If it moved 23 light years in 3 years, it was moving at a v about equal to 8 light years per year, or about 8 times the velocity of light, since light travels 1 light year per year of time. So it looked like our velocity was 8 times the velocity of light. How can this be? Several models have been proposed, but the most likely idea is that the blob is moving not across our line of sight, but rather almost along it. But this seems even more preposterous because it would have to be moving even further to get to the position we observe now. However, the state of affairs is easily seen with the aid of the following diagram. Let's imagine that the blob emits photon 1 that we see at the top of the radio map when it is at point O. The photon starts traveling the enormous journey in a straight line towards the Earth, and it reaches point A after 100 years. Thus, A is 100 light years from O. Meanwhile, the blob moving at almost but not quite the speed of light in the direction of B, gets to B after 101 years. At B, the blob emits a photon, photon 2, as it has been doing all along, of course, towards the Earth. The second photon also travels in a straight line towards the Earth. Photon 2's path is parallel to photon's 1 path, while the actual source, i.e. the blob, continues on its own path at the angle shown in this diagram. At this point, looking at triangle OBA, the blob appears to be 8 light years from A, but the photon emitted from the blob at B is actually only 1 year behind the original photon observed to be coming from A. So from the point of view of the Earth, the blob appears to emit light originally from the direction towards A, and once that light gets to us, after billions of years, the light from B will be 1 year behind. Our model is saved. But how does all this relate to our sense of cosmic history? When the nature of the galaxies finally came to light about 75 years ago, people were awed by the serene grandeur that these island universes presented. Stately in their motions, rotating once every 100 million years, each containing up to 100 billion stars, they presented a picture of eternal tranquility. In fact, a popular cosmological model up to the 1960s was the steady-state theory, which posited an unchanging, eternal, infinite space where new and old objects stood side by side, uniformly spread throughout the far reaches of the universe. The discovery of the quasars sounded a death knell for this idea. Indeed, the implications of these observations were so bizarre that many astronomers refused to believe the interpretation that we just presented, and instead sought to explain the redshift, which implied vast distances and hence stupendous energy output, by other means. All these ideas failed, and rather reluctantly for many, scientists had to accept the picture we have painted here. When hundreds of other quasars were found, one fact stared us in the face. The nearest quasar remained 3C273, over 2 billion light years away from us. Where were the more nearby ones? Why weren't they distributed uniformly in space? The answer seems clear. The quasars evolve in time. Remember that we see 3C273 as it was billions of years ago because of its incredible distance. Thus, if a nearby quasar once existed, say, in M31, we would be seeing it as it was a mere million or so years ago. But suppose the quasar turns into a galaxy after a while. If quasars were a product of the early universe, only the most distant ones would still be visible, since we would be looking at them at a time when they were active. So it is quite possible that if someone were to observe our Milky Way from a galaxy close to 3C273, they would see the celestial fingerprint of our galaxy as a quasar, since the light they would be observing from the Milky Way would be 2 billion years old. And from their vantage point, 3C273 would be a nearby and probably a normal appearing galaxy. So quite literally, The quasars are Empyrean time machines, leading us back into the early history of the universe, which, as we have seen, seems quite different from the regions of space that we see today in our neighborhood. They portray a story of vast reservoirs of energy that seethe in X-rays, optical and radio waves, and they open our eyes to the cosmic history that is part of our common heritage.